Alright, how's it going, guys? This is going to be a video about a Scratch project that I made and the concept behind it. It's a neural network, and I just wanted to explain how I made it. Currently, I just posted it a couple hours ago, so it's like brand new. It's this one. Actually, let me go to the home page first. Okay, so um, yeah, you can see like only me has seen this. So what I've been doing recently is I've been really intrigued in neural networks, which here I can actually go here. This is the wiki explaining what a neural network is. If you don't know what a neural network is, you could read all this. It's basically just a computer intelligence that mimics the way the human brain is constructed, um, with like the neurons and all that stuff. So here's a good image. So there's three layers here. A complicated and like better neural network would have many layers and it would be much bigger than this, but this is just kind of like a diagram of it. Mine looks similar to this, except you can have as many inputs, as many outputs, and as many hidden as you want. It took me a really long time to figure out how to code something like that, where you can just kind of change it with a change of a single number. Um, but I figured it out finally, and that's why I'm sharing this because it's like a finished product, and like I'm really proud of it. So basically these input layers would be like, imagine for this diagram here, it'd be pretty simple to explain. Imagine these are like one-dimensional eyeballs, right? Like you have like a little guy and he can see in a straight line, and the farther an object is away from him, you get a value. So like let's say an object, and then this would be, there's like, if this was like the head, right? There'd be like an object, let's say there was an object right here. This would be like a distance of 2, and then this would be a distance of like infinity or whatever, because there would be nothing in the way. Um, then it would take these numbers and multiply them by these lines, which are called the weights. And this would be multiplied by the weight and then added to this. Now this, I just realized this, uh, the neural network here is not showing exactly how it should look. As you see, these weights are only connected to 3, where a neural network, I don't know if the word proper neural network would be good to use, but I'm just going to say that a proper neural network should have, uh, each node is connected to each other node in the next layer, so there'd be 4 weights. So anyway, it would take, this node would be calculated by saying take input 1 times weight 1 plus input 2 times weight 1 for, well, weight 2, but it'd be weight 1 for this node, and then plus a bias. So there's like an invisible bias for each node. Same with the output. So in this case, it'd be uh, hidden node 1 times weight 1 plus hidden node 2 times weight 2, all the way down, and then you would add a bias, and then and then you would uh, use an activation function, like a sigmoid function, to calculate the node at the end. So it can basically, like, if you have a number that's like 0 and you put it in the sigmoid function, you get a zero point 0.5. Uh, Actually, that's not the real beauty of it. It's when you get anything higher than, well, anything to infinity will always be squashed down to 1. A better way to do it, let me just look it up. Sigmoid func function. A better way to explain it would be to see the image. So here is a good sigmoid function example. So here's like a number line. So you put in 0, you're going to get a zero point 0.5. You put in 2, you get this number, and it squashes it. So when this number goes into infinity, you get 1. It gets closer and closer to 1, never reaching it. And then the same with this, but it'd be 0. So we use this for each node so that the numbers, because you're multiplying numbers and adding them together, it can like explode and the numbers can get really big. And you don't really want to do that. You want to keep all the numbers pretty consistent so that your output is a range that you can manage. So it's not just random. Because when you're taking an input of, let's say, a distance, that distance can easily be, 1 pixel long if you're doing a two-dimensional um, thing like the scratches. This is two-dimensional. Um, it could be one distance long. Actually, I'll be over here. It could be like so. Here's the track, and I have multiple tracks. Now I'll show it off in a second. But if the creatures are facing to the right and they're right here, this distance is clearly huge. And then it turns left a little bit and now it's facing this and it hits right here. This distance is much smaller than this distance with only a tiny difference or like a tiny input. So you want to squash the value so that it doesn't really um, like imagine if you're using your mouse and your mouse's sensitivity is insanely high and you want to do these little moves. Like I can put my mouse up pretty high right now. So you see how fast it's moving. I'm barely moving my mouse. Like I can still control it, but it definitely feels weird. So if I lower it down, now I'm moving my mouse around my whole desk and it's only moving this big. So anyway, I'm getting sidetracked. So that's how the math works behind the neural network. And then this output would be something like you want the creature to move or something. So you take input and you get an output. And then after you do that, you want to find the desired, or like if you want the creatures to move along a track, the desired output would be something that would continue the creature along the track. Or what I have it doing is basically it has a score, and the score goes up the more the creature moves. So a problem with mine is that if the creature finds a certain range of weights that causes it to spin in a circle and never touch a wall, then technically it's thinking that this is the better or the best creature because it's moving forever. So I haven't figured out a way to calculate that out. Like for humans, for us humans, we would definitely know a creature is doing the best, or we would categorize it as being the best if it's going along the track forever and ever, and we wouldn't like it to spin. But to put that into math, it's kind of confusing because you would have to calculate the last position where it was, and then take the distance, which I can do. And actually, now saying that out loud, I realize I could definitely do that, but I'm not going to do that right now. Um, so that's just the overview of what this thing does. I'll go into the nitty-gritty, and then I'm going to dive into the code at the end of it, but I'll show it off right now. So what I have is there's a lot of numbers here on this. And actually, I want to switch to the other track, which I didn't have to go in here for that. Um, Also, a disclaimer, it might bug out. Let me refresh the page. Something with Scratch, when you make this full screen, um, it for some reason bugs out the character or the little creatures. Uh, so let's see if oh crap. Let's see if it's working. Wait, is that default? Oh, it is default. Okay. So, whoops. Okay, and then we just press C. Okay, so right now, okay, so here's the creatures. So let's put the mutation rate down to something lower. And I'm going to put the turbo. So it runs faster the less there are because it's less calculations and it's just better to put it on turbo. That's why the first thing I have here says turbo. So these are all these little creatures have this, but a little bit different shaped inside of them with all different weights. That's why they're all moving in a different position and um, reacting differently to the environment. The first thing you play around with in this is the mutation rate. Um, and that is basically saying that when all of them die, uh, oh, I'm skipping ahead of myself. Each one has a score, right? I said that earlier. And that score goes up based on how much they move. That's how I've calculated the score. I can go inside and show that, which is right here. Here's the score calculation. And right here, I have it changing score by move times 10. So it moves by a certain amount, and I have it set to 5. So it's moving about at speed of 5 in Scratch. If you use Scratch before, you know kind of how fast that is. So I have the score going up by 10 just so that it has a little bit more reward. I had this by 10 because originally I had a score change by 1 based on each tick of this score. So not only was it being rewarded for moving, but it was also being rewarded for existing on the track the longest or staying alive, really. But I took that out because of a reason I can't remember, but um, that that was mainly to incentivize the little creatures or little AI to not hit the walls, which you see they're still doing. And actually, this is not really improving too well. It's only on 45 though, so never mind. It's fine. It usually takes around 400 or so generations to really understand the turns and all that stuff. Um, anyway, so that's the score. Then what it does is whatever creature has the best score, so the biggest score, it will put it down in fitness. Now, when you're in the thing, when you're inside the code like this, for some reason, Best AI loves to just label itself like this, so it's always blocking it. But back here, it's fine. You can see. So I don't know. That's a weird thing that happens. Um, so here's the fitness. And fitness is basically the biggest or the best score, how good the best creature is doing. So I could title this best score, but in most AIs or in most neural network stuff, it's usually called fitness. So I just did that too. Um, and basically, okay, so now that I covered the score, when they all die, it'll copy the best score. Well, actually, not when they die, but it'll copy the best score of the creature. Sorry, not the best score. It'll copy the weights of the best creature, is what I'm trying to say. All the weights inside its little brain is being copied to a location, and then the next batch is created based on those copied weights. Okay, so I kind of got interrupted there. So I don't know how long that was, but you can probably tell by the generations just all of a sudden jumped. And I'll probably cut out some of that. Anyway, doesn't matter. So I think I was talking about the way it was copied. So I'm just gonna restate what I said. I was talking about basically the best creature. So one of those actually will copy its weights onto a location, which the location is called best weights, and then it's a list. And then it will copy that list all onto all the creatures and change those values by the mutation rate. So if the mutation rate is 0, you'll see they're all the same creature um, because they're all the same copy from the best weights. Then if I change this up, this is going to take forever, so I'll just press space. So one of the features I have is pressing space. That will basically skip the generation. It'll kill all of them. So here I did that. And now you see each one of those weights, each creature has a tiny bit of change. If I put it all the way up, you see they're very radical. And I don't want to do that too often because some of them will start spinning really fast. So look at these guys. So the best one, the best creature has a fitness of 1092. And as you saw, it probably got around that point. So it's learning, it's understanding these kind of curves. And another aspect of the code is this hidden size. So if you press H, it'll prompt you um, how many nodes, how many hidden nodes you want. I'm going to leave it at 2, and basically that is again it's this. So I'm basically compressing the inputs, which there's 3 inputs. Oh, I haven't even talked about the inputs yet, but there's 3 inputs, compressing them kind of compressing them into 2 hidden nodes and then taking that and turning them into 3 outputs. So uh, making the hidden nodes bigger gives them a better, and I have it stated here, it gives them like a bigger brain, a higher potential of intelligence. But if you think about it, and I can actually, well, I don't think I'm gonna need the word, or not the word, the paint. Here, I'll leave that running and I'll just kind of do this. But basically, or I'm saying I don't think I need this to describe it actually, but I'm just taking it out anyway. So imagine, yeah, I'm not gonna need it. I'm still gonna write it though. Imagine you have 2 hidden weights or 2 hidden nodes. Since I have 3 inputs and 3 outputs, the weights are gonna be it. There's gonna be um, the input weights are gonna be multiplied from input and hidden, which means that that's gonna be 3 times 2. So it'll be 6. So I'll just write that right here. Oh gosh, I'm using the mouse to draw, so it's going to be weird handwriting. Plus, um, then there's going to be the biases are going to be the same amount as the nodes for the hidden. So that's going to be plus 2. And then it's going to be the hidden times the output. So plus 6, because there's also 3 outputs. Oh my gosh, plus 6. And then the last one, the biases for the outputs, which there's 3. So 6 plus 2, so 12, 13, 14, 15, 16, 17. So it's going to be the odds of getting a creature, well, for the, if you think about it like this, it makes sense and it doesn't make sense. So basically, the odds of the creature being smart is 1 out of 17. It really isn't, because the weights are going to be a random number between 1 between 1, or between -1 and 1. So all the point zeros and the point 3, 2, 1, 6, 5, all of that. Um, so the odds are really kind of infinite times this. But anyway, this is the main factor of how um, the chances are somewhat. So as you see, if the brain gets bigger, um, and I think I skipped ahead of myself. They spawn in with a random weight. I forgot to say that, I think. But anyways, that's why I'm saying all this random stuff right here. So if it's a bigger brain, imagine it was just double all the stuff. Then this would be 12. This would be 4, and then 12, and then 6. So this is just basically double, right? Yeah, it'll be 38, I think. No, 30. Oh my gosh, my brain. 34. So 1 out of 34. It gets bigger and bigger and bigger, is basically what I'm saying. I don't even know if I'm doing the math right. Um, anyway, so what's the next thing I was going to talk about? Talk about the mutation rate. I have a lot of stuff here if you're interested in reading it. It's just about how the thing works, basically. Um, and before I started this video, I was planning on making like a whole list on my other monitor and kind of like really being professional about it. But it's just a simple little video. I'm not going to put that much effort in it. Um, anyway, the next thing is this. And then the track. And you saw how the track works. You click the track, it goes to the next track. The next thing is this, and then I'll just recap on the buttons, I guess. So this one right here is current best or all-time best, meaning if it's set on current best as default. I think it's default. I'm not entirely sure. But current best is basically it will take the fitness. Oh, actually, I just realized that they're doing pretty well now. So if I press space, let me see how they're doing. Okay, so if I put this up, yeah, so it's pretty weird. So it's on 99. Around 400 or so, around 400 generations. Um, Putting this on a high mutation rate so that they'll be very different from each other still results in a lot of them doing really well, which means that it's almost like they're really good at being really good is like the takeaway from that. Because as you see, if I restart it from 99, some of them just spin out control, which means that this increase, let me put that back here, that increase is affecting the nodes a lot. And the the more smart they get, the less this kind of has an effect. So anyway, that was just a side thing. I was talking about this. So this is when it's set to 0, these are going to be or all the creatures will be copied from the current best weights, which are the ones they're working with right now. So it's the best AI, which is 10, the 10th node, or the 10th AI, which actually, so it's in order, but it's not really the 10th AI, because it was probably the 10th AI from a previous, well, now it is the ninth, but um, it doesn't copy the weights every single time. It only copies weights when the fitness is higher than it was before. As you see, it's going up right now. If I press space, see, it still says 9, but the ninth creature doesn't have a higher fitness. It was the ninth from the previous. So anyway, putting it to all-time best is I actually have a list that has a saved function or a saved list that has weights from one that I ran a generation of 763. So if I put that right now and I put this off and I'll restart them, you'll see these guys are all the same creature, and you see they work very well. So this was just a saved run. It's seven. It doesn't show 763. I could implement that, but it doesn't really matter. And then the fun feature is if now you have a really good creature, but if you want to keep getting it better, you can just switch it back to current, and then if I restart it, it's going to use that current. Also, I don't know why it slows down sometimes like this, but anyway, it's going to use that all-time best as the current. So now from this point on, it's going to keep building on the last, and the last was this guy, and then the next one it would be two last times ago it would have been this guy. So anyway, now let's. I think it's time to go into the code. It was really confusing. If I go back to here, you can see that I've had multiple attempts. Well, this one's one I'm working on next, but and it's using the same function because I got it right once. Now I don't need to build a new one. So yeah, these were all just attempts, and I really tried on them. And every single time they were promising, and then there was one or two numbers that just didn't work out, uh, and the whole thing just broke. This one, I tried to put everything in three lists, so that it could work, but it gets way too complicated. Then this one, I tried to make everything in seven lists. Yeah, seven lists, all separating all the inputs, all the input weights, all the input biases, all the hidden weights, all the hidden biases, blah, 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 all the outputs. Then this one was a little bit, oh, this one was very similar to this one, except when I was coding it, I kept track of everything I was doing. I was very professional with this, and it messed up, which I can't remember why it messed up, but I know if I just look at it, I'll remember. Um, it's very similar to the one I have now, actually. Oh, right. Uh, oh, actually, I don't know why it messed up compared to the first one. But anyway, the real beauty behind the new one is that I don't have single list for all the hidden. I set it so that when I created the lists, um, they are, if I click open on one of them, oh no, that's best ways. That's not going to show it. Let's say hidden nodes. If I move this around, you see it says AI because it's for every single clone. Just like if you know Scratch, then you know that you can create um, things. Like if I create a variable and call it whatever, I can say for all sprites, so it's a global variable, or I can say for this sprite only, a local variable. And when you put it to this sprite only, it not only does it only for this single sprite right here, but it does it for all the clones, which are considered their own sprites too. So now all the math is really simple because I'm not shifting the list down by the size of the inputs. And I'm just shifting it down. I'm just reading off the list basically for each clone. Okay, so where to begin? I guess to begin where the code begins, which I'm having some mouse lag right now. It's acting weird. It's like jumping all around. I don't know if you can see that being picked up, but look how weird that is. It's like jumping. Okay, anyway, I think it needs to be charged. I also, my mouse just broke recently. It sucks. It's like a $70 mouse, and it works fine. I can click and everything, but the mouse wheel has like it has an axle, right, where the wheel is rotating around, and that either popped off or it snapped off. I can't tell. And I tried taking the mouse apart, but I don't have the right supplies, and so I couldn't even see on the inside. I'm pretty sure it snapped off, which is really upsetting. So I can't use the scroll wheel at all. Um, anyway, that doesn't matter for the video. I'm talking too much. So here's where the code begins. Actually, it does need to be charged. Give me a second. Let me plug this in. I think that's the problem. It's really acting up right now. That's why I'm actually doing something for it. Um, Okay, look at that. See, much better. So um, here's where the code begins. And what it does is, or maybe I should talk about the more important stuff. This is just the setup and all that. Um, oh, I didn't even talk about the buttons. I kind of did. Uh, I'm all over the place, man. Well, you can see the buttons in the code if you ever look at it. I guess the real, if you came to this video like looking to figure out how um, to code this, then this is I should talk about the code rather than the stupid buttons. Um, by the way, there is no backpropagation. I do not have any backpropagation on this. I don't know why I'm circling this. There is no backpropagation on the neural network. What backpropagation is, if you don't know, which it might even have it right here somewhere. Um, Maybe, but I can't see it. Backpropagation is, and if I click on this, it'd be good. Basically, there's a feed forward, which means that you take the information from the input and you feed it, or do the calculations, multiply it by the weight and blah blah blah. Feed it into the next layer. Then you feed it into the output layer. That's the feed forward process. The learning process comes by seeing what the difference is from that output layer to what you want, and then seeing so you know the distance you need to travel or the desired or the error, which is the desired output minus the expected output, or yes, prediction minus expected. And then knowing that you do this like reverse stuff, which is like with calculus and derivatives and all that to figure out what how much you need to change a weight to get closer to the desired output. Um, and it's really complicated. It might not even be that complicated, but I've tried figuring it out. I just cannot. In what's it called? In Jupyter Notebook, in like another coding thing, I have followed tutorial and I can see how it works, but to code it in Scratch is a whole nother story. It's a whole nother language, and it's I'm not intuitively understanding it yet. I just know what I need to have rather than I need to have it. So anyway, I don't know how long I've been recording, but I know it's already too long. So let's start with the actual neural network. I know that if the best way to learn is to kind of follow along and do it yourself while I'm doing it, but I really do not want to code this thing again. So I'll just talk about it, and you can take screenshots or you can go to the place and then you know look at it yourself and copy it. Uh, I said in the text box over here somewhere that um, oh, is this personal? I just realized I'm in personal. Yeah. Um, I said in the box that feel free to remix it and really like dig in. This is a very um, universal neural network. The only things you need to change is the sensory input, the movement, and the score. The neural network will work with basically anything that takes sprites to accomplish it. So calculating like data, like if you want to use a neural network to determine what type of something it, like what type of car there is based on the wheel size, you know, that's not something this thing is designed for. I bet it could be changed, like a slight change, and it'll work, but I'm not really sure. It's really just creatures. That's why I named it creatures, AI creatures. It's like if you want a guy going around a track, it could do that. If you want someone to dodge your mouse based on the distance of your mouse and the position where it is and the direction it's facing and all that stuff, and you want physics on it, it can handle all of that. You just need to change what it's seeing, how it moves, and what makes the robot good, which is the score. So let's talk about the neural network. Here is the neural network. These three are the neural network. And I have two of these are, so this is to calculate the hidden nodes, and this is going to calculate the output nodes. Um, Actually, let me start over here. Let me just start with the more intuitive, better learning experience. Um, the first steps it does is it will set, so I have variables saying what input weight I'm on, or well, what input I'm on, what hidden I'm on, and what output I'm on. And then in here, it determines which type it is, the input, the weight, or the bias. And it will go through all the hidden while it's calculating the hidden nodes. So if I take this apart, this right here will calculate all the hidden nodes. No matter how many you have, it will do this because it will repeat the nodes. So it's right here, the repeat for how many nodes there are, and it will change this variable based on this repeat function. So it's basically going down the list of hidden nodes. And then it's the exact same. These are the exact same. These are the exact same. The only difference is that this is talking about the hidden. So you have hidden node, current input, and then you see down here it's output. So it's output node, current hidden. It's basically just the one step farther. So if I go back to this, um, when I'm calculating the hidden nodes, wherever you see hidden in the output one, it's going to be output. Wherever you see input, it's going to be hidden. You get it? I think you can, if you're clever enough, you can understand what's going on here. Um, and right here, this change hidden node, or the current hidden node it's on, basically. Um, this is the input times weight function right here. So this is the inputs, and this is the weights. And then right here is the bias, add the bias, and then sigmoid it up, and then replace that hidden node with the hidden node that we just calculated. Same with output. I know that none of that might help with creating it on your own. So that the best thing you could do, because I'm not going to really dive into it too much, is to come to the project um, and look at it and dissect it or remix it. It's simple thing is to remix it. If you want to know how it's done, then you can look at it and all that. But honestly, this works pretty well. Like it's kind of just multi-purpose, and you just need to change a few things. So when it comes to these three things, I'll go in depth with these so that you know what to change. Um, anyway, so that's the neural network. So I guess now we're on to this. I missed something here. Sorry about that. It's also these. So if you see when the clone starts, um, this AI is here. So for every tick, it will run the neural network. It will run the inputs. It will run the movement. So that's down here. But we have to set up the neural network first. So that's what these are for. Because these neural networks are referencing the items in the list, but we have no list when it starts out, so we have to create the list. So don't worry about reset, that's just these things, and it resets the score, so each new created creature has a score of 0, which is what you need. And then right here, it has two different types of setups. This runs right on the first generation because it's setting up them with random inputs, which is these. Um, okay, and then sorry about that. And then this one is the new setup. So this is over here, new neural network setup is the new calculated um, creatures or new calculated neural network. So as you see, item current copy, which is just the number. So here, let me copy this. It's like current. So item 1 of best weights, item 2 of best weights, item 3 of best weights. It copies all the best weights, and it does it for the appropriate places. So the input weights and all that. And then here is the mutation rate times a random number. So this is what changes it. So if the mutation rate is 0, then it's adding 0. It will be a complete perfect copy for every clone. Okay, now we got that out of the way. Oh, crap. So let's see if I just test it. I'll let this run while we're doing it. Wow, that one immediately, well, it didn't immediately get, it only knows to go straight for right now, but I'm surprised how far it went on the first batch. So I'll just let that run. Then next is the sensory input. Now the sensory input is actually pretty complicated. It takes it's basically like 3 eyeballs, which actually I won't run this. I'll show you what it looks like. Actually, I won't be able to, but here's the creature, a little adorable creature. And then here's what I call a ray. And it's just a tiny little dot, and this is basically like a photon. Uh, and it tells the creature how far away it is from a certain direction. Right now in the code, since I have three inputs, that is corresponding to the three types of rays there are. Uh, I can use this for this. So here's your creature. Oh, shapes. Okay, here's the creature. And I have a ray that's going straight. So there's one type. I have a ray that's going at a 45 degree, which is like that. And then I have another ray that's going a 45 degree. And they actually start from the center, but I just have them like this. And these three will tell a certain distance until it hits a wall. Or, this or is a big or it gets too far. It gets the length of 60, I think. I think I have 60. Yeah, 60 right here. So because I don't want it to calculate all the way to the wall because it's computationally taxing. It's basically the rays are moving a step every tick, which I have here, a step. If I change this to 5, it'll move a distance of 5 every tick, and which is less computational, but still, there's a certain point where it's going on forever, and it will just make the whole program just shut down. It's too much for it to handle. Um, this, do I want to talk about this? I guess I do. Um, so each ray, each line, each one of these lines is really, again, is really just a movement every tick by one. So it's like moving one pixel, kinda. Even though it's going diagonal, like we can still consider it moving one pixel, where it's really not. But anyway, we'll just say that. Um, and it will do this for, I don't need to do that. It'll do this for, like, let's say the creatures are here. It'll do this for like 30. That's probably like a distance of 30. When it comes to a bend, it changes. It gets closer, it gets a smaller number, it gets farther away, has a bigger number, blah, 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 blah. So it changes it to that ray, that little, um, what did I call photon? I could call it photon, actually. That might be better, but I'll just leave it as ray. Man, if I go through this, it'd be really complicated. Uh, sorry, I don't know if I'm gonna go through this. It's just complicated. It's just a pretty convoluted, that's the word, pretty complicated way of just creating an array in three directions and then uh, and saving the position it started on, and then at the end of it, right here, at the end of it, right here, it turns back into the AI and goes to the position it started at, so that the if I didn't have this, it would just, when the first ray moved, the creature would now be there, and then it would die because it hit the wall. So it just goes back to the position, if that makes sense. Um, that's sensory input for sight. That's the only input I have is sight. Other inputs could be the direction it's facing. I did test that earlier. It takes a long time for the computer or for the neural network to figure out that because um, using the direction it's facing, remember it's a value, where is it? It's a value from 0 to 360. Well, okay, it's a value, it stops at 180. But so facing up is numerically very different from facing right and very different from facing down, which we know that it's not that different. Like that's a huge number. Like a increase is an increase of 15, is increase of 180. It's a very big difference. But for us, we really just know the direction. Obviously, this and this are small differences, and this are large differences, and the direction. Like we have a sense of all of this is the same vibe. It's a big circle. You're getting the same vibe from each number. You just know which way to go. Instead, the number it takes in the number weird, but it will get there. It just takes a while for it to understand because it's not only does the um, the neural network or the inputs have to be intuitive, like the distance. It also, or no, not only does it have to be um, well, yeah, it has to just be intuitive for the robot to learn. Because if it's some random number that's constantly changing, that doesn't seem to really be um, consistent, then it will never find what it needs to do. It's like imagine if the distance constantly changed every movement, but it didn't change appropriately. It changed like to a random number. It would never make sense of that. It's analogous to our eyes focusing and unfocusing like super rapidly every second, and we just cannot understand what we're seeing, or they're moving around and we can't understand what we're seeing, or all that stuff. Um, so you can add more sensory input, uh, and that's one of the beauties of it. If you have like a fighting game, you can take this and make it into a fighting game. So you can have your health as an input, so that your health determines how the neural network does its actions. So let's say you had health and you had a swing, then it will probably swing more um, when its health is low, or maybe it'll just figure out that it should just swing as fast as it can all the time. But so that if anyone gets close, it'll hurt them, and it's like a defense. Or maybe they'll put up their shield when the health is low, or something like that. Um, the next one is movement. I named it movement because that's the only thing they're really doing is moving. This is better described as um, like character behavior, or like character actions, or actions in general. Um, And let's see, where is actions or movement? Okay, so here it is. So here's the output nodes. Remember, I only have three outputs, so here's all of them. So I don't need to have any fancy variables in here. I could just say output one. Oh my gosh, man. I just had like soda and some fries, and so like I'm getting like hiccups, or not hiccups, I'm like about to burp. Um, so that's why I keep like talking funny. Anyway. So I set these variables. I don't need to I don't need to create variables for these items. I just do that just so it's nicer looking when I'm worrying about the actual movement. So you move, move, turn, 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 turn. It's just easier to look at instead of having this be here. So, and then if I ever want to do any fancy stuff with move, like if I want to make move times move, I just have a little thing instead of a big thing. So right now, the input that's coming out is a range from 0 to 1. Um, that's what the sigmoid function does. It compresses it. Remember, it's a 0 to 1. Uh, so they can never go backwards. But I could make them go backwards by just taking the value of 0 to 1 and subtracting zero point 0.5 to it. So you know how the middle is zero point 0.5, right? So you subtract zero point 0.5, and now the middle is here. And then 1 becomes zero point 0.5. You don't want that. You want a full increase. So you can multiply also by 2, and now the zero point 0.5 becomes 1. And so in turn, you get this. Here's the x, this line, the middle line. The x, is that x? Well, here it says t, but that's x and this is y. And then this is not going to look right, but it'll be like this. Yeah, that's actually pretty good. And then multiplying by 2 would be like if you didn't multiply by 2, this height and this height would be 0 0.5, yikes, 0 0.5, and then this would be negative 0 0.5. You multiply by 2, this becomes 1, and this becomes negative 1. So there you go. So that's how you turn a sigmoid function into from a 0 to 1 to a negative 1 to 1. But I don't want them to go backwards. Like there's no need to. They can always be going forward. If you have a creature that's fighting, it would be nice to face forward and go backwards so they can like, avoid, they can fight still when facing forward, but they can also walk backwards to avoid whatever's coming at them. But I don't need that. And I also have that multiplying by 5, so it's going at a 5 speed. And then the turn radius right here is basically, or it is basically the turn radius. This is based on how fast you're moving. So I have it at a 1 to 6 ratio. So this allows them to turn these tight corners. If I do something like 1, then you'll see even if when they start, like none of them are turning. Like the turn is super slow. Like you'll never, at this, you'll never see any creature spinning around because when they try to spin, they'll hit the wall before they can actually get around because they're moving too fast. But then I put that to like 100, and you can see they're going crazy. They have the ability to turn really fast. So I leave it at 30 because I've found that's a pretty good number. Maybe more like 25 might be the best number. Um, so again, with this, you could have more outputs. The inputs and the outputs, you can really have anything you want, and nothing will, it won't learn. The, the only way you'll have a best creature is with the score, which I did kind of talk about the score, but here I'm gonna go into depth. Um, so right now I have if touching equals 1, then kill the clone. Before I had this as if touching black, kill the clone, but because these are all running at the refresh rate right here, well, this one isn't specifically for that reason, but actually, you know what? I can have that though. Let me see if this runs the same. I can have it on because I have this now. They're all running at a run without screen refresh. So they all do their thing before the next frame really. And even though it keeps track of the timings, like it will do sensory input first and neural network, sometimes they overlap. I'm not sure if that's exactly what's happening, but sometimes it does a weird number. And so instead of having it touching, because remember, it touches with the ray. So if it said if is touching black and it was also calculating the position of the ray, it might kill the clone without it actually touching it. So then I have it setting to touching as 1 after it's done all the rays. So right here it turns back into an AI and then it determines if it's touching or not. I don't really need it, but because of the inconsistencies of these, or maybe it's my lack of understanding, that I have it like that. The next thing is the space bar. So here's what I was talking about where like you could just reset the position, just by, oh, whoops, none of them are gonna live. So we press space, it just, I can keep resetting um, the simulation. And then the next one is, this is where it's calculating the fitness. So if this current creature's fit score is greater than the fitness, then copy weights, set fitness to score, and set best AI to ID, which they all have their own ID. I just realized, do I? No, okay. I was gonna say, should I put fitness on top of weights? But no, it's not needed. So here, this is all, well, yeah, so these two are killing the clone. If you have something where you never need to kill the clone, which doesn't make sense because it only copies weights, it only refreshes them when they're all dead. So I guess you need it, but this is basically just this is just for this track. You wouldn't need touching if you didn't have something that it was gonna die on when it touches, right? If you didn't have a track. If you had a big open empty field, you won't need this because that's there's no point of that. But if you had something like a a platform like this, it'd be similar to this, and then this is like considered lava or something, and they're kind of like these creatures in a dungeon running around and killing things, and then oops, one of them falls off, you kill them off. So, and then this one again is just copying the fitness. So this you always need this for this creation. And then right here is where you determine your error, or we consider it, or like I consider it for this current uh, project, I consider this. I totally lost my train of thought. Just you put your own what you think the AI is doing good here. So again, with the fighters, you'll change the score based on how many opponents they killed, right? And so then that clearly is the better creature. Or if they're eating food because they're like rabbits or something, you change the score up when they um, find food and eat it, or, something like that. So that's all of that. The last thing is the copy weights function, which is over here. Oh, there's also this to create all the AI. You can just look into this when you need to. Um, I'll explain that in a sec. So here's the copy weights. Basically, this is taking, Wait a minute. Oh, okay, sorry. Because I was like, it's not saying which um, AI it's referencing to, but that's because this is a function within the each AI. So they all have the ability to copy weights onto the best weights, but it will only copy weights from the best AI anyway. So it's only called once. Actually, it's not called once. It's called every time someone gets a better fitness. So if I go to it, right off the bat, you'll see it should change pretty drastically. But then, see, it's not changing from 20 because 20, no, nothing is getting better than 20. Right now, no one's doing better than 20. So it will only change when someone overtakes someone else. So that's that. And then the last thing is over here. Now, this is the reason I don't have it connected to anything is because this is only like a one-time use thing. It's very rare. This is how I set the all-time best. Uh, I don't know why this is so far away. And then I have an example here. So this is only gonna work if you have a remix version of it. You are the creator. Like if I click this, or if I was coming from an outside one or perspective, like if I was you came in and you click this when you're in the code, if you refresh the page, the all-time personal best weights would not be the same. It would be the ones that I saved because I own the code and you're refreshing the code. So you remix it, you get the ability to use this, and you just click it, and it will take the best weights and put it in and save them into a place that will always be accessible. And then all you gotta do is do this, change that. So that's the whole thing. I'm trying to think if there's anything else I could talk about. Maybe the AI setup. Um, this is basically determining, see how it's active right now? It's because it's waiting, which is, it's right here. Wait until after it's done all this, which you can read. It's just setting up the fitness and input size and all that stuff. Um, and then the reason that the hidden isn't here is because I have the hidden here after it's asked, which I could also put this over here. I don't need it here. I don't need it to, actually I'm going to do that right now. I don't need it to set the input size and all that for every single batch. I don't need to, but if it wasn't there and I changed it, it wouldn't break or anything. So let's do that and save. So now when you go into code, that's going to be like that. So anyway, it's waiting for me to put down the mouse because when I click it first time, this is the starting point. As you can see, start X and start Y. This is where all the creatures are going to start from. And then you also need a way it's facing, and I could do like another point and figure out the a tangent of the distance and all that weird stuff to figure out what direction it is. But I just thought it's so much easier to when I click next, just have the original sprite face to the next point, and then all the other ones are going to spawn in at that direction. That's really simple. And then so reading it down, when you say wait until mouse is down, you have to have wait until not mouse is down at the bottom of that function you're using. Because if one click for us, we would think it's just one click, but Scratch is stupid sometimes, and it will like call this function like 20, 30,000 times within that one click because of like it can do that for some reason, and it will do that. So it will wait until the mouse is down, and then it will run all this code, and then it will do that again and again and again for where is it? For is it? Do I only have a function here? I guess here. I thought I called this many times. Oh no, I only called it from the beginning. Anyway, that's the long and short of it. I also have it the pen setting so that you can actually see where you're clicking, and then it goes away when the creatures spawn in. So there's that. That's about it. I will put links in the description to this page and all that, so go check that out. And yeah, thanks for watching. If you have any questions, by the way, I said this down here. I hate using this because my stupid mouse is broken. Um, but I set it down here. Just ask me any questions you have about this. I remember when I was trying to figure this all out, I was super eager. I was super interested in this, the concept of neural networks, and Scratch is the only place I'm really good at coding with. Anything else, it's like confusing for me. And nobody, you search networks, and no one here. Oh, not the S. None of these people, they have good things. Like this one was the first one I found that I really liked, that like worked, but they're not helpful. Like it says stuff but it doesn't say exactly how. This is also where I got the 45-degree angle from, but they don't really explicitly say how it's done. And the guy's tutorial, oh no, here, look at this. I said this. You should totally make a tutorial on how you made this, blah, blah, blah. I think I looked into it and there is a tutorial from this dude. I forgot his name. Let me see. Yeah, Martin. Yeah. There's a tutorial from this dude, but it was like, I think there's no words. Go check it yourself. It's not very helpful, I think. Even though not to be mean to the guy, but this one's interesting. This one is a little more advanced to me. Oh gosh, hold on. Hit a mute button. That was super loud. It's a little, well, I won't run it. You can test this one yourself, but it's advanced because it has these lines. I can implement that, but it's a little laggy. I don't know how he didn't get it laggy. And I'm pretty sure that he also, or she, it could be she, um, check fitness and die, calculate nodes, initially. I don't think they have a backwards propagation or back propagation. That's the thing. New neural network right here, maybe? Yeah, I don't think they have back propagation like me, which is surprising because I thought they did. So I thought they were more advanced, but maybe they're not. So, oh, maybe here. When I receive tick, uh, output speed. Yeah, no, I'm guessing this is movement or something. Directional wheel. They're definitely, whatever they're doing, I think it's a little, okay, sloppy is not the right word. It's a little more than it's necessary. And the only reason I feel like I've gotten such a very optimized code is purely because I've coded this thing like 4 times and I figured out what works and what doesn't. And even though it looks like a lot of things, each chunk is super like it does what it does. It's not all these weird numbers calling back. It's like most of the stuff does what you would think it should do. So anyway, that less of bragging about my code, and you can go check it out for yourself. So yeah, so thank you for watching this tutorial kind of thing. Anyway, bye.